Good morning, good afternoon, and good evening to everyone who joins us from around the world. We're so glad you're here. This is Andrew and Renee. Welcome to the Stacks series.
It is wonderful to be back with you.
Today, we are exploring the turbulent, high-stakes, and scientifically complex quest for the holy grail of physics, room temperature superconductors. And honestly, looking at this stack of research we have in front of us, holy grail almost feels like an understatement. It feels like we're talking about the philosopher's stone or, alchemy.
It really does have that mythical quality to it, doesn't it? But the thing is, unlike alchemy, this is very much grounded in rigorous physics.
Right?
Although, as we're definitely going to see today, that line between, let's say, groundbreaking physics and wishful thinking can sometimes get a little blurry.
A little blurry. That is putting it mildly. I mean, this story we're getting into today, it has everything. It has viral internet sensations, it has actual betting markets on scientific outcomes, and then it goes into high-level academic fraud and even government investigations.
It's a wild ride.
It is. But before we get into the drama, and folks, there is so much drama, we really need to ground ourselves. We need to understand what we're actually chasing here. Because when I hear superconductor, I picture this giant humming machine in a lab basement somewhere.
Yeah.
But the dream is,
Oh.
it's so much bigger than that, right?
Oh, much, much bigger. I mean, to really understand the dream, you have to understand the fundamental problem with our current reality.
Okay.
The entire modern world, our lights, our computers, the very device you are listening to this on right now, it all runs on the flow of electricity. But the way we move that electricity is, to be frank, incredibly inefficient.
And that's because of resistance, right?
Exactly. Resistance. Think about the copper wiring that's inside your walls or, the big high voltage lines you see stringing across the countryside. Copper is a fantastic conductor, relatively speaking, but it's not perfect.
Not perfect.
Not at all. As electrons, the little particles that carry the electric charge flow through that copper wire, they're constantly crashing into things. I always picture it like a crowded hallway between classes at school.
That is a perfect analogy. It's a great way to think about it. Imagine that school hallway. The electrons are the students, and they're all trying to get from one end to the other.
Right, to their next class.
Exactly. But the hallway isn't empty, is it? It's full of obstacles. In this case, it's the atoms of the copper itself. And to make matters even worse, those atoms aren't just standing still. They are vibrating.
Vibrating? Why are they vibrating?
Yes, because of thermal energy, heat. Any temperature above absolute zero means the atoms have energy, and they express that energy by jiggling around. So the warmer the wire, the more those copper atoms are buzzing and shaking back and forth.
So the students are trying to run down a hallway where the lockers and the walls are all shaking.
Precisely. So as our little electron students try to run through, they keep colliding with these vibrating obstacles. They bump into the lattice of copper atoms.
And every single time they crash, they lose a bit of energy.
Correct. They lose momentum, and that lost energy gets transferred to the lattice of atoms, which makes those atoms vibrate even more.
Ah, so it's a feedback loop.
It is.
Yeah.
And that extra vibration, that extra energy in the wire, that's what we feel as heat. If you touch your laptop charger after it's been plugged in for a while, it's warm, right?
Yeah, sometimes it's really hot.
That warmth is literally wasted energy. It is the cost of doing business in a world with electrical resistance. It's the sound of billions of tiny collisions.
And when you scale that up, from my one laptop charger to the entire planet, that waste must be absolutely massive.
It's colossal. We lose a significant percentage, somewhere between, say, 8 and 15%, depending on the grid of all the power we generate, just trying to move it from the power plant to your house.
So we build a giant power plant, and then almost a sixth of what it makes vanishes into thin air.
It simply evaporates into the air as heat. It warms up the planet in a way that does nobody any good. Now imagine a material where that doesn't happen, a material where that hallway is.
Yeah.
Well, where it's wide open.
A perfect empty hallway. So a superconductor.
Exactly. In a superconductor, the resistance is zero. And I want to stress that number. It's not low. It is on almost zero. It is zero.
Okay, stop there for a second, because zero is a very, very absolute number. In the real world, nothing is perfect. Nothing is ever truly zero. How can it actually be zero?
This is where we have to leave the world of classical physics, the physics of baseballs and planets, and enter the quantum realm. It's a completely different set of rules.
Okay, so what's happening at the quantum level?
In a superconductor, the electrons stop acting like individual students running down the hall. They pair up. These are called Cooper pairs.
Cooper pairs, like a buddy system.
It's exactly like a buddy system. It's a bit counterintuitive because electrons are both negatively charged, so they should repel each other.
Right, like trying to push two magnets together the wrong way.
Yes. But in certain materials, at very low temperatures, something else happens. When one electron moves through the lattice of atoms, its negative charge actually distorts the lattice around it. It pulls the positively charged atomic nuclei toward it just for a tiny fraction of a second.
So it creates a little dent in the structure of the material.
A dent or ripple. A wake. And that little region of concentrated positive charge attracts a second electron.
So the first electron creates a wake, and the second electron is sort of surfing on that wake.
In a way, yes. And once they are paired up like this, they undergo a fundamental change in their quantum nature. They stop being fermions and start acting like bosons.
Fermions, bosons. Okay, you might be losing me.
Let's stick with the hallway analogy. Fermions, like individual electrons, are antisocial. They have to follow a rule that says no two of them can be in the exact same state at the same time. That's why they all have to take slightly different paths down the hall, bumping into things.
Okay, so they're individualists.
Right. But bosons are different. Bosons are. They're collectivists. They love to be in the exact same state. Once the electrons form these Cooper pairs, they become bosons.
Yeah.
And then they can all condense down into a single coherent quantum wave.
A single wave.
A single wave that flows through the entire material. It's like all the students in your hallway suddenly hold hands, turn into ghosts, and just float through the walls and lockers without ever touching them.
No collisions.
Zero collisions.
No heat.
Zero heat.
No loss.
Precisely. And we've known this is possible for over a century. The Dutch physicist Huyck Kamerlingh Onnes discovered it in 1911. We have superconductors right now, today, in our labs and hospitals.
But there's a catch, isn't there? A really big one. Otherwise, my toaster cord wouldn't get warm and the whole world would be different.
The catch is the environment. To get those electrons to pair up and act like ghosts, you have to quiet down all those vibrations from the atoms. You have to essentially freeze them in place.
How cold are we talking? Winter in Chicago, cold.
We're talking surface of Pluto, cold. For conventional superconductors, we are talking temperatures near absolute zero. That's minus 459 degrees Fahrenheit or minus 273 Celsius.
Okay, so impossibly cold. What's the other option?
Or you have to crush the material under immense pressures, pressures comparable to the center of the Earth. You use a device called a diamond anvil cell to squeeze it.
Which, practically speaking, makes it completely useless for running a power line to my house. I can't wrap my home in liquid helium or build power lines out of diamond anvils.
Exactly. It requires massive, expensive, energy-intensive infrastructure just to keep the material in its superconducting state. It's a paradox. You spend a ton of energy to save energy.
So the Holy Grail, the thing everyone is chasing, is a material that stays in that magical superconducting state at room temperature and ambient pressure.
Yes. No giant freezers, no diamond anvils, just a wire that you could hold in your hand at room temperature that has zero electrical resistance.
And if we find it, if someone actually cracks that code,
it changes civilization. I don't say that lightly. It is a genuine paradigm shift for humanity. It would revolutionize the power grid. We could generate solar power in the Sahara and ship it to London with absolutely zero loss.
Wow.
It would mean batteries that last for weeks and can charge in seconds. It would enable things like maglev trains, levitating, fictionless trains that are cheap and ubiquitous. It would completely change medical imaging, computing, everything.
It's the kind of technology that literally divides history into before and after.
It absolutely is. And because the stakes are so astronomical, we're talking trillions of dollars, multiple Nobel Prizes, the entire future of energy. The race to find it is incredibly intense. And that intensity, well, it does strange things to people.
That's a good way to put it.
It creates hype, it creates desperation, and sometimes, as we'll see, it creates outright fraud.
Which brings us to our stack of sources for today, and it really is a wild mix. We have reports on a viral sensation from South Korea called LK99 that took over the internet.
I remember that summer well.
We have a very grim investigation report from the National Science Foundation here in the U.S. regarding a major scandal. And then we have some very dense but very promising, rigorous new papers that are using machine learning to hunt for these materials.
It's the full spectrum of the scientific experience, really. You have the hype, the crash, the fraud, and then the slow, steady, incremental climb of actual progress.
So let's jump into part one, the promise of this stuff. I was reading through the source from Swissinfo, and they made a reference that I think just perfectly captures the vibe of this entire search. They mentioned the movie Avatar.
Ah, yes. The unobtainium.
Right. The entire plot of that movie, the reason humans are traveling across the galaxy to fight giant blue aliens on the moon Pandora, is to mine this rock called unobtainium.
Which is a great name for something you can't get.
Exactly. And the reason it's so valuable, the reason they're willing to go to war for it, it's a room temperature superconductor.
It's a great pop culture touchstone because it really highlights the immense economic value. And if you recall in the movie, there's that scene where the corporate bad guy, Selfridge, he has a little piece of the rock on his desk. And what is it doing?
It's just floating, it's spinning there in midair, no strings attached.
That isn't just movie magic. That is based on real fundamental physics. It's a property called the Meissner effect.
Okay, let's unpack that. Because floating rocks becomes a huge part of our story later on. Why does a superconductor float? What's actually happening there?
So when the material becomes a superconductor, it doesn't just gain the ability to conduct electricity perfectly, it also becomes perfectly diamagnetic.
Diamagnetic, what does that mean?
It means it expels magnetic fields. It actively pushes them out from its interior.
Pushes them out, like a force field.
Exactly like a force field. Imagine magnetic field lines are like invisible arrows shooting out of a magnet. A normal material, like wood or your hand, lets those arrows pass right through. But a superconductor is like a perfect shield. It bends those arrows around itself. It absolutely refuses to let the magnetic field penetrate its interior.
And that pushing contest between the magnet and the superconductor creates a physical force.
Precisely. If you place a magnet over a superconductor, the magnet's field pushes down, and the superconductor pushes back up with an equal and opposite force. The result is levitation.
But it's not just floating loosely, is it? I've seen videos where it seems stuck.
Yes, that's the key difference. It is quantum locked. Because of some complex effects involving tiny imperfections in the material, some magnetic field lines can get trapped. The superconductor is then pinned in space. You can turn the magnet upside down, and the superconductor will hang there, suspended in midair, fighting gravity.
So that's the visual proof, the smoking gun. If you claim you have a room temperature superconductor, the first thing people are going to say is, okay, show me the floating rock.
Usually, yes. That is the dramatic demonstration everyone looks for. But beyond the cool floating trick, it's the practical applications that are really driving all the funding and the research. Let's go back to the MRI machine example for a moment.
I have.
Have you ever had an MRI?
I have, yeah. It's incredibly loud. You're in this tiny tube. It feels very claustrophobic. And I know from the bill that it's incredibly expensive.
Right. The reason it's so expensive and so bulky is largely due to the cooling system. Inside that giant machine are massive superconducting magnets that generate the incredibly strong magnetic field needed for imaging. But to keep them superconducting...
You have to keep them at Pluto temperatures.
Exactly. They are bathed in thousands of liters of liquid helium.
Liquid helium, that sounds exotic and expensive.
It is. It's a non-renewable resource, actually.
Right.
We get it from natural gas drilling. And we face global helium shortages periodically. The engineering required to keep that helium at minus 450 degrees Fahrenheit is just massive.
Mm-hmm.
You need complex vacuum flasks, cryocoolers, specialized insulation. It's a beast.
But if you had a room temperature superconductor...
You could strip all of that away. The magnets would just work. No liquid helium, no cryocoolers, no massive insulation.
So the machine itself could shrink?
Drastically.
Yeah.
You could have MRI machines that are the size of a conventional CT scanner. You could even have portable ones. Imagine putting an MRI scanner in an ambulance, scanning a stroke patient on the way to the hospital.
Wow.
Imagine having them in rural clinics in developing nations that could never afford the infrastructure or the constant supply of liquid helium.
Yeah.
It would completely democratize high-end medical diagnostics.
That's a huge deal for global healthcare. And you mentioned the power grid earlier. I feel like we all just sort of take it for granted that when we send electricity from a power plant to a city, a whole bunch of it just disappears along the way.
It dissipates as heat. We talked about that 8 to 15% loss. In a world who's desperately trying to manage its energy consumption and fight climate change, just throwing away up to 15% of all the energy we generate is...
Yeah.
It's a tragedy.
And a room temperature superconductor would slash those losses to basically zero.
To near zero, yes. It would also make renewable energy so much more viable. I mean, think about it. The biggest problem with solar and wind is intermittency, right? The sun isn't always shining, the wind isn't always blowing.
And the best places for them are often far away from where people live. The sunniest places are deserts, the windiest are offshore or in the middle of nowhere.
Exactly. You can't currently generate massive amounts of power in the Sahara Desert and send it efficiently to London or Berlin. The transmission losses over that distance would be too high. But with a superconducting global grid, distance becomes irrelevant. You could have a network where the sunny side of the Earth is always powering the dark side.
It really does sound like the unobtainium of our world. It sounds, frankly, too good to be true. And as we all found out in the wild summer of 2023, sometimes unobtainium is just, well, unobtainable. And this brings us right into part 2, the summer of LK99.
Ah, yes. The summer the internet decided to become amateur solid-state physicists.
Seriously, I remember this so vividly. It was late July 2023. I woke up, checked my social media feeds, and suddenly everyone was talking about rocks. A team from South Korea, led by researchers named Lee and Kim, dropped a couple of scientific preprints on a website called ArcFuff.
And ArcFuff, we should say, is a place where scientists can post their research before it's been formally peer-reviewed. It's for getting ideas out there quick.
And they weren't just claiming some small improvement. They were claiming they had hit the absolute jackpot.
They were. They claimed they had synthesized a material they called LK99. The LK stands for Lee and Kim, and the 99 apparently refers to the year 1999, which is when they said they started this research. And their claim was astonishingly bold. They said it achieved superconductivity at temperatures up to 400 Kelvin.
Which, for context, is about 127 degrees Celsius, or 260 degrees Fahrenheit. That's not just room temperature, that's hot enough to boil water temperature. That's baking inside a pizza oven temperature.
And crucially, at ambient pressure. No diamond anvils required. They were saying, essentially, we did it, we found the Holy Grail, here's the Philosopher's Stone.
And the recipe they published, it wasn't some ultra-complex nanofabrication process involving lasers and particle colliders, was it?
No. And that was the hook. That's what really set the world on fire. It was a solid-state synthesis, basically grinding up powders and baking them, that, at least in theory, you could do in a well-equipped high school chemistry lab.
What was actually in it?
It was a lead apatite structure, specifically a copper-doped lead oxyapatite. The recipe called for taking a mineral called lanarkite, which is a lead sulfate, and another compound called copper phosphide, grinding them into a fine powder, mixing them, sealing them in a vacuum quartz tube, and then baking them in a furnace for several hours.
Basically, baking rocks? And that apparent accessibility is what drove the absolute frenzy. It wasn't just major university labs trying to replicate this. It was DIY enthusiasts in their garages. It was Twitch streamers setting up live feeds of their furnaces.
It was a completely unique moment in the history of science.
Yeah.
We saw the gamification of a scientific discovery. People were live streaming their furnace temperature gauges. There were prediction markets like Polymarket where people were betting real money, thousands and thousands of dollars, on whether LK99 was real.
I remember watching that. The price of a yes share would swing wildly based on a single tweet from some obscure lab in China or a rumor posted on a forum.
It was pure chaos.
And the fuel for that entire fire, the thing that made it go viral, was a video. The South Korean team released a short, low-resolution video showing a small, black, pebble-like chunk of this LK99 material. And in the video, it appeared to be levitating over a magnet.
A visual proof.
Oh, yeah.
Smoking gun, or so it seemed.
I must have watched that video 100 times. And the rock wasn't totally floating, was it? It was kind of twitching. It looked wobbly.
It was canting. One edge of the sample was clearly touching the magnet, acting as a pivot point, while the rest of the little rock was lifted up. To the layperson, and even to many hopeful scientists, it looked like the Meissner effect. It looked like the material was actively pushing against the magnetic field.
But you, looking at this as a professional scientist and the broader scientific community, what one of our sources calls the Swiss consensus, you aren't popping the champagne just yet.
Oh, far from it. Immediate and intense skepticism is the immune system of science. It's what protects us. And Dirk van der Merel, the experienced physicist from the University of Geneva mentioned in our sources, pointed out almost immediately that the theoretical explanation in their paper was, well, it was incomplete. It didn't hang together.
It wasn't a polished, peer-reviewed paper. It was a preprint, a first draft.
Exactly. And the data they presented was messy.
What do you mean by messy?
In a clean, well-controlled experiment, the graphs you plot are usually smooth. The relationships between variables are clear. In the LK99 papers, the data points were scattered all over the place. The graph showing the drop in resistance wasn't a sharp, sudden cliff like you'd expect for a true superconducting transition. It was a lumpy, gradual slope. It just looked dirty.
But because the recipe was supposedly so simple, the global replication race started immediately. We had labs in China, India, Europe, and the US all rushing to bake their own batches of LK99. It was like a global science bake-off.
It was. And this is where the story gets really interesting from a scientific perspective. Because baking rock sounds simple, but solid-state chemistry is notoriously fickle. It's like baking a very complicated cake. A tiny change in temperature or a slight impurity in your ingredients can completely change the outcome.
In different labs started getting different results.
Wildly different results initially.
Right. I have the list here in our notes. A team at Southeast University in China, they were one of the first. They reported seeing a big drop in resistance at 110 Kelvin. That sounded really promising at the time, right? The internet certainly thought so. The phrase, "we are so back," was trending worldwide.
A drop in resistance is a good sign, certainly.
Yeah.
But first of all, 110 Kelvin is minus 163 degrees Celsius. That is nowhere near room temperature. And second, and this is the crucial part, they did not see the Meissner effect. No levitation, not even a wiggle.
Then you had the National Physical Laboratory in India, CSIR-NPL. They synthesized the material, they checked it with X-ray diffraction to confirm the crystal structure was what the Korean team claimed, and they found absolutely no superconductivity at all. Nothing. It was a complete dud.
And then the real heavy hitters came in. The Max Planck Institute for Solid-State Research in Germany. This is one of the most prestigious and respected research institutions in the entire world.
And they didn't just mess around with the grind up some powder and pray method, did they?
No. The team at Max Planck, led by Pascal Pufel, they're experts. They realized that the original Korean recipe created what's called a polycrystalline sample.
Polycrystalline meaning?
Imagine making a cookie by just pressing a bunch of different crumbs together. That's a polycrystal.
Yeah.
It's a messy jumble of different crystal grains, all with different orientations and with boundaries between them. It's not pure.
So what did the Max Planck team do?
They used a more sophisticated method called floating zone crystal growth to grow pure single crystals of LK99.
Like growing a perfect diamond instead of a lump of charcoal.
Exactly. A continuous, perfect, unbroken lattice of atoms. And when they succeeded, the crystals they made were beautiful. They were transparent and a deep shade of purple.
Purple crystals. That really does sound like something out of a fantasy novel, the purple crystal of power.
It does. But the result of their tests was very, very grounding. When they took these pure, perfect purple crystals, the idealized version of what LK99 was supposed to be, and they tested them, they found that it was not a superconductor. It wasn't even a metal. It was an insulator with a resistance in the millions of ohms.
An insulator. That is literally the opposite of a superconductor. A superconductor lets electricity flow with zero resistance. An insulator stops it dead.
Correct. Pure LK99 is an insulator. It fights against the flow of electricity.
So wait, if the pure stuff, the actual LK99 is an insulator, then how in the world did the original team see a sharp drop in resistance? And what about the floating rock? This brings us to part 3, the crash. Why did LK99 fail so spectacularly?
Well, by mid-August of 2023, the verdict was in. The dust had settled, and the scientific community had figured out the culprit. And it wasn't the lead apatite itself. It was an impurity in their sample.
An impurity. So basically dirt.
In a manner of speaking, yes. Remember the recipe. You mix lanarkite and copper phosphide and bake them. Well, chemical reactions in a furnace are rarely 100% efficient. They often leave behind unreacted starting materials or create unwanted side products.
Leftovers.
Exactly. And one of the key leftovers in the original team synthesis was a compound called copper sulfide, formula 22 Sellers.
Copper sulfide. Okay. Why is that specific impurity so tricky? What's special about it?
This is a classic case of nature playing a cruel, cruel trick on a group of researchers. Copper sulfide is a very well-known material, and it has a very specific, very well-documented property. It undergoes what's called a first-order structural phase transition at a specific temperature.
It changes its shape on an atomic level?
Yes. The atoms rearrange themselves. And that transition happens at around 104 degrees Celsius.
104 Celsius. Wait a minute. That's right around the temperature where the original Korean team said they saw this amazing drop in resistance.
It's almost exactly the same temperature. And when copper sulfide goes through this phase transition, its electrical resistance drops sharply by a factor of 1,000 or more. It doesn't go to zero, not even close, but it is a dramatic drop.
The light bulb moment. So they were measuring the resistance of their entire lumpy, dirty sample. They saw this big drop and they thought, Eureka! We found a room temperature superconductor.
That is the consensus, yes.
But really, they were just measuring the mundane chemical properties of the leftover copper sulfide impurities in their dirty sample.
They were measuring the ghost of the copper sulfide. They misinterpreted a standard, well-known chemical property of an impurity as a revolutionary quantum property of their main material.
Wow. That explains the electricity part. But what about the video? What about the floating rock? I saw it canting. It was definitely pushing against the magnet.
He saw a rock standing on its tiptoes. This is where we have to make a very clear distinction between the true Meissner effect and just regular old magnetism.
Okay, unpack that. Because to my eyes, if it floats, it floats. What's the difference?
A huge difference. As we said, the Meissner effect leads to quantum locking. It's a very strong, stable, three-dimensional pinning effect. What we almost certainly saw with that little LK99 pebble was a combination of two much more common effects: ferromagnetism and diamagnetism.
Diamagnetism again. You said it was a weak repulsion.
Yes. Most materials are weakly diamagnetic. They will be slightly repelled by a strong magnetic field. But LK99 also seems to have bits of ferromagnetic material in it, impurities that are strongly attracted to a magnet, like tiny bits of iron.
So parts of the rock were being pulled down and other parts were being pushed up?
That's the idea. The ferromagnetic parts were being pulled down towards the magnet, pinning one side of the sample. Meanwhile, the diamagnetism of the rest of the sample created a weak repulsive force, pushing the other side up. It created a precarious balance where it looked like it was levitating, but it was just a result of competing magnetic forces.
Physicists call it ferromagnetic half-levitation. It's a known phenomenon.
It looks cool, it looks impressive, but it's not superconductivity.
So the lesson here seems to be, check your purity. And maybe don't trust a grainy, low-resolution video on the internet as proof of a world-changing discovery.
The broader lesson is also about the importance of the peer review process. ArXiv is great for speed, but it completely bypasses the traditional gatekeepers of science. Peer review exists to have other experts look at your work and say, hey, this looks interesting, but did you consider that your signal might just be copper sulfide? Before you tell the entire world you've solved the energy crisis.
Right. It felt like we were watching the peer review process happen live, in public, on Twitter. And while it was ultimately disappointing, it was also kind of beautiful to see the scientific method work in real time. A claim was made, it was tested by the global community, it was found to be incorrect, and science moved on.
Absolutely. It was a false alarm, but it seems to have been an honest mistake born out of hope and perhaps some flawed measurements.
Honest mistake. That's a key phrase, because that brings us to a much, much darker chapter in the superconductor saga. While LK99 was a case of misinterpretation, Part 4 deals with something else entirely, something that makes baking rocks in a garage look positively innocent.
Yes. Now we have to talk about the Ranga Dias scandal.
This is just wild stuff. So Ranga Dias is not a YouTuber. He is, or was, a rising star physicist, a professor at the University of Rochester. And unlike the garage baking vibe of LK99, this was high-level, prestigious, top-tier academic science.
We're talking about papers published in Nature, papers published in physical review letters. These are the absolute top journals in the world. Getting a single paper in Nature can make a scientist's entire career.
And in 2020, Dias made global headlines. He published a paper in Nature claiming he had achieved room temperature superconductivity.
He did, in a material called carbonaceous sulfur hydride. But like so many of these claims, it required immense pressure.
And people believed it, right? It was published in Nature, it went through the gatekeepers, it was peer-reviewed.
Initially, yes. It was hailed as the breakthrough of the century. But almost immediately, other physicists who specialize in these high-pressure experiments started scratching their heads. They couldn't reproduce the results.
Which happens, right? Sometimes these experiments are just very tricky.
It happens. But then they started looking much more closely at the data in the published paper itself. And they started noticing things that just didn't add up. Eventually, the National Science Foundation, the NSF, the U.S. government body that funds this kind of research, launched a formal investigation.
And we have the report from the NSF Office of Inspector General right here in our stack. It is not light reading. It's a 50-page document that alleges fabrication and falsification of data.
Those are the nuclear weapons of accusations in academic misconduct. And the report is incredibly specific and damning. It focuses very heavily on one particular graph in one of the papers, Figure 2A, which showed a property called magnetic susceptibility.
Okay, so let's zoom in on this Figure 2A. What was so wrong with it?
It comes down to the noise. When you measure anything in the real world, temperature, voltage, a magnetic field, your instrument is never perfect.
Yeah.
There's always a little bit of static, random, tiny fluctuations in the signal.
Like the subtle fuzz or hiss you get on an audio recording.
That's a great analogy. Exactly. And that fuzz, that noise, is mathematically random. It follows a specific statistical distribution. What the independent reviewers and the NSF investigators found in Dias's data was that the noise, well, it wasn't noisy in the right way.
What do you mean by that? How can noise be wrong?
It looked too perfect. The fluctuations seemed to follow a pattern that was inconsistent with the data analysis method he claimed to have used. To the trained eye, it looked like the noise had been added manually or generated by a computer algorithm to look like noise, rather than being the genuine, messy result of a physical experiment.
So it's like if I told you I flipped a coin 100 times and I wrote down the results, but you analyzed my list and realized I had just typed heads, tails over and over in a perfect pattern. It's not truly random.
Precisely. Real randomness is messy. This data was too clean in its messiness. It was a huge red flag that suggested deliberate manipulation.
Oof. And that wasn't all. There was a copy-paste issue, too. This one, to me, sounded just shockingly audacious.
It is genuinely shocking. The investigators found that a graph of electrical resistance data in a 2021 paper from his group appeared to be identical to a graph of data in Dias's own PhD thesis, which was from years earlier.
Okay, so maybe he just reused an old graph for a presentation.
But the problem is, the 2021 paper was supposedly about a material called manganese disulfide. His PhD thesis was about a completely different material, germanium selenide.
Two completely different materials.
Completely different elements, different structures. Yet the curve of the graph, every specific wiggle and bump and data point was identical, pixel for pixel.
That is impossible. That's like me taking a picture of a sunset in Hawaii today and having it match pixel for pixel a photo of a sunrise in Norway that I took 10 years ago. It can't happen.
It's statistically impossible. The only plausible conclusion is that he took the old data from his thesis, maybe changed the labels on the axes, and presented it as new, groundbreaking data for a completely new material.
That is just devastating. And the fallout wasn't just the journals retracting the papers, was it?
No. Both the Nature paper and another in Physical Review letters were retracted, which is a huge public stain on a scientist's record. But perhaps the most damning thing of all is that 8 of the 11 co-authors on the Nature paper wrote a letter to the journal asking for the retraction themselves.
His own team, his own students and collaborators turned on him.
They did. They stated in their letter that they were left out of the final data processing and review process, and that when they raised concerns with Dias, he dismissed them. They effectively said, "We didn't know he was doing this. We were deceived too."
I can't imagine being a graduate student in that lab. You think you're working on a project that's going to win a Nobel Prize, and then you find out your boss is allegedly copy-pasting data from his old thesis?
It's a tragedy for those young scientists, and it does incredible damage to the entire field. It erodes public trust in science. Science relies entirely on a foundation of integrity. When you have high-profile retractions for fraud like this, it makes people cynical about the next legitimate breakthrough. It makes it harder for honest researchers to get funding because now everyone is hyper-suspicious.
It casts a very long, very dark shadow. But we have to remember that for every one of these scandals, there are thousands of legitimate scientists out there doing the hard, slow, plodding work of actual discovery.
Absolutely.
And we have a fascinating new paper in our stack that illustrates exactly how that real science works. It's not flashy, it's not going to go viral on TikTok, it's not baking rocks in a garage, but it's real.
Yes. Let's pivot now to part 5, the hard science. We're looking at a theoretical paper titled Design of a 60.8K Superconducting Hydride LIM-MgZr2H12.
Okay, that name does not exactly roll off the tongue like unobtainium. LIM-GRCZr2H12, but let's break it down. What exactly are we looking at here?
We are looking at a class of materials called hydrides. For the last decade or so, hydrides, which are compounds that are very rich in hydrogen, have been the absolute best bet for finding high-temperature superconductors.
Why hydrogen? What's so special about the simplest, lightest element in the universe?
Well, it comes back to those atomic vibrations we talked about right at the start, the phonons. The prevailing theory of superconductivity, called BCS theory, says that these vibrations of the atomic lattice actually act like a kind of glue that helps bind the electrons into those Cooper pairs.
The mattress analogy.
Yes. The lighter the atoms in the lattice, the faster and more energetically they can vibrate, the higher their frequency. And these high-frequency vibrations are much better at gluing the electrons together. Hydrogen is the lightest element there is. So a lattice made of hydrogen is like a very bouncy, very fast-moving trampoline. It's excellent for superconductivity.
Okay, so hydrogen is good,
Hmm.
but usually don't these hydrides need those insane diamond anvil pressures?
Hmm.
I remember reading about a quest to create metallic hydrogen that needed pressure like the core of Jupiter.
Yes, that has been the huge roadblock. Hydrogen is a gas at normal conditions. To
Yep.
force it into a solid metallic lattice, you usually have to crush it between diamond anvils to millions of atmospheres of pressure. That's why all the previous hydride records, which got tantalizingly close to room temperature, were ultimately impractical. You can't live your life inside a diamond anvil cell.
So what makes this new theoretical paper different? What's the new idea?
This paper proposes what's called a quaternary hydride. It uses 4 different elements: lithium, magnesium, zirconium, and hydrogen.
And the goal is to get it to work at ambient pressure, to
Yeah.
basically take the pressure off.
Exactly. They're trying to use chemical pressure instead of brute force physical pressure.
Yeah.
The idea is that by carefully arranging these other atoms, the lithium, magnesium, and zirconium, in a specific crystal structure, they can pre-squeeze the hydrogen atoms from the inside, forcing them into a configuration that's good for superconductivity without needing the external press.
And the secret sauce here seems to be something called lithium doping. Doping sounds like something out of sports again. What does it mean in materials science?
It just means adding a small, precise amount of a different element to your main material to change its properties. Think of it like seasoning a soup. You have your base, the magnesium, zirconium, hydrogen structure, and then you strategically sprinkle in a few lithium atoms in specific places.
And what does that pinch of lithium do to the soup?
It does 2 crucial things, according to their calculations. First, lithium is also a very light element. It's the 3rd element on the periodic table.
Right.
So adding it helps maintain those high-frequency lattice vibrations that we want.
Okay.
Second, and this is the more important part, it acts as an electron donor.
It gives away its electrons.
Yes, it generously adds more free electrons into the mix, specifically near a critical energy level called the Fermi level.
The Fermi level. Okay, remind us what that is in simple terms.
Think of all the electrons in a material as being like water in a bucket. The Fermi level is the surface of that water. It's the energy level where all the action happens, where electrons can easily move around and conduct electricity. To get good superconductivity, you want a high density of states at the Fermi level. You want lots of electrons available right there at the surface, ready to pair up and carry the current. The lithium doping boosts that density.
So this is all theoretical. They designed this material on a computer, they ran the simulations, they crunched the numbers on this LiMG8R2H12 soup. What was the predicted result?
Their calculations predict a critical temperature, or Tennessee of 60.88 Kelvin at ambient pressure.
60.8 Kelvin. Okay, let's do the conversion again. That's roughly minus 212 degrees Celsius.
Or about minus 350 degrees Fahrenheit.
That is still very, very cold. That is not room temperature. That is colder than the coldest night in Antarctica. So why are we excited about this?
Because of the pressure, or rather, the complete lack of it. Finding a hydride that is theoretically stable and superconducting at 60 Kelvin at ambient pressure is a massive theoretical step forward. Most of these high-performing hydrides simply fall apart or lose their superconductivity the moment you release the pressure.
So it's a proof of concept. It's a design that says, hey, we think we figured out a way to build these high-performance hydrogen cages so that they can work without the diamond anvil.
Exactly. It's steady, incremental progress. It's not a sudden leap to the finish line, but it's moving the ball down the field in a very calculated way. The paper notes that the material has a high figure of merit, a value of 1.56, which they describe as showing outstanding potential for this class of materials.
This is how real science usually happens, isn't it? It isn't a sudden viral video of a floating rock. It's a team of theorists running simulations for months and publishing a paper that says, we think if you add lithium here, it will get 10 degrees better.
Precisely. It's iterative, and it's built on a deep understanding of the underlying physics.
But that brings up a question for me. If we aren't just guessing and baking rocks anymore, how do we find the right combination? Because there are practically infinite combinations of elements on the periodic table. Lithium, magnesium, zirconium. Why not sodium, iron, and carbon? How do you even know where to start looking?
That is the perfect question, and it brings us to part 6, the reality check, and the increasingly important role of machine learning and artificial intelligence in this search, because you are absolutely right. The periodic table offers far too many combinations for humans to test one by one, even on a computer.
And this was a mind-blowing study to read about. We have a source here detailing a study where they didn't just test 10 or 20 materials, they screened 100 million compounds.
100 million potential compounds. This is the brute force approach, taken to its logical extreme. Instead of waiting for a lucky accident like LK99 or a brilliant theoretical insight like the hydride paper, they just trained an AI to do the work. They taught it the laws of quantum mechanics and then told it to look at the electronic structures, the phonon bands, and the thermodynamic stability of millions upon millions of potential materials.
It's like having a million physicists working around the clock for 1,000 years, but you condense all that work down into a few weeks on a supercomputer.
That's a good way to put it. And the computer found something fascinating and, well, a bit sobering. It identified what scientists call a Pareto front.
A Pareto front. That's a concept from economics and engineering, isn't it? It means there's a fundamental trade-off.
Yes. It's a situation where you cannot improve one variable without making another one worse. The AI found that for conventional superconductors, there seems to be a very strong trade-off between thermodynamic stability and a high superconducting temperature.
Unpack that for me. What does that trade-off mean in practice?
It means you can have a material that is very stable, meaning it won't fall apart, explode, or decompose at room temperature and pressure. Or you can have a material with a high superconducting transition temperature. But finding both of those desirable properties in the same material at ambient pressure is incredibly rare. They seem to be mutually exclusive.
So nature is actively fighting us. The universe is saying, you can have a stable rock, or you can have a high-temperature superconductor, but you can't have a stable, high-temperature superconducting rock.
At least not with the conventional electron-phonon mechanism that BCS theory describes, which is what the AI was trained on. The data strongly suggests there may be a ceiling. Despite checking millions of compounds every week, the AI isn't finding anything that is both stable and has a critical temperature much above 50 or 60 Kelvin at ambient pressure.
That's absolutely fascinating. It's almost like the supercomputer's coming back to us and saying, I've checked everywhere. Stop looking in this specific box. The answer you're looking for, room temperature, it probably isn't in here.
It forces us to be realistic. It suggests that if a true room temperature superconductor does exist, it might require unconventional physics that we haven't fully modeled yet, a different glue for the electrons. Or it might be a material so structurally complex like a twisted multi-layered nanostructure that even our current AI models are too simple to find it.
Or, and this is the bummer to think about, maybe it just doesn't exist.
It is a possibility we have to accept. Nature might just say no. But even if we hit a hard ceiling at, say, 100 Kelvin, that is still a transformative technology compared to where we started with liquid helium.
How so?
Because liquid nitrogen boils at 77 Kelvin. And liquid nitrogen is incredibly cheap. It's literally cheaper than milk. If we can get superconductors to work easily and cheaply at liquid nitrogen temperatures, that's still a massive revolution for things like the power grid.
That's true. We don't necessarily need room temperature to change the world. We might just need cheap to cool temperature. But let's play devil's advocate for a second. Let's say tomorrow someone defies the AI, defies the odds, and they find it, the real unobtainium. A genuine room temperature, ambient pressure superconductor, stable, and everything. Are we ready to just, wire up the world?
This brings us to part 7, the very real, very unsexy challenges of implementation. And the answer to your question is a resounding no.
Why not? If I hand you the magic wire, why can't we just start using it?
Because the magic wire might not be a wire. Look at the types of materials we've been discussing all this time. They are ceramics. They are hydrides, packed into complex crystal structures. What happens if you try to bend a ceramic dinner plate?
It shatters into a million pieces.
Exactly. Brittleness is a huge, huge engineering hurdle. The reason we use copper for wires is because it's ductile. You can stretch it, you can bend it, you can wind it into tight coils for a motor, you can hang it from a giant pole and let it sway in the wind for 50 years.
But you can't do that with a brittle ceramic. If we tried to make a power line out of it, it would just snap the first time a strong wind blew.
Very likely, yes. We would have to develop entirely new manufacturing techniques. Maybe you'd have to put the superconducting material inside a protective metal cladding or grind it into a powder and pack it tightly into a tube. It's a massive engineering nightmare that could take decades to solve.
And what about cost and abundance of the materials?
That's the next huge factor. The Swiss Info interview touched on this perfectly. The physicist Dirk van der Moraal made the point. We aren't going to make a car out of gold.
Right. If this magic superconductor requires rare earth elements like lutetium or expensive elements like zirconium, we simply can't use it to replace the thousands upon thousands of miles of grid lines.
We need millions of tons of this stuff to rebuild the world's infrastructure. If the material depends on zirconium or lithium, we have to ask, Do we have enough zirconium? Is the supply chain secure? Or are we just trading a geopolitical dependence on oil for a new dependence on rare metals mined in only a few countries?
And finally, there's durability. You mentioned the stability issue earlier.
Yes. Power lines sit outside in the elements. They get rained on, they get snowed on, they get baked by the sun. They are constantly interacting with oxygen and moisture in the air. Many of the hydrides, the very promising materials we just discussed, are chemically unstable in air. They react violently with moisture.
So you hang your brand new, super expensive, superconducting wire, the first rainstorm comes, and your wire turns into a pile of rust or sludge.
A superconductor that degrades in a week is utterly useless for the grid. We need materials that can last for 50 years with minimal maintenance. So even after the eureka moment of discovery in a lab, there would be decades of material science and engineering required to turn that laboratory curiosity into a robust, usable product.
It really puts all the hype into perspective, doesn't it? The gap between we found a weird signal in a lab and we have a functional levitating train network is absolutely massive. It's not just one step, it's a marathon of 1,000 more steps.
It is. But that doesn't mean we shouldn't be excited. The fact that we are now using AI to screen millions of compounds, the fact that we were getting better and better at designing hydrides, the fact that the scientific community can so quickly and efficiently spot the frauds and the errors, it is all progress.
It's the journey, not just the destination. We are learning more about the fundamental rules of the universe, atom by atom.
Precisely.
And speaking of the journey, I think we've covered an incredible amount of ground today. From the floating mountains of the movie Avatar to the wobbly floating rocks of YouTube, through the dark corridors of academic scandal, and into the bright, clean rooms of supercomputing and machine learning.
It's a powerful reminder that science is messy. It's a human endeavor. It is full of false starts, dead ends, and human error. But, and this is the important part, it is also self-correcting. The LK99 saga showed that beautifully. The community came together, it tested the claim, and it found the truth.
And the search goes on.
It does. And who knows? Maybe the next time we have this conversation, the AI will have found that 1 in a billion compound that breaks all the rules. Or maybe a graduate student somewhere working late in the lab really will bake the right rock.
One can dream.
Indeed.
Before we wrap up, thank you to all our partners, sponsors, and scholars who made this podcast and the research possible. We're truly grateful for your support.
And to our listeners, thank you for being part of this journey with us. If you enjoyed today's episode, be sure to subscribe and follow Stack Studios for more informative content. And support us on Patreon.
Until next time, stay curious, keep learning, and let the search for wisdom guide you forward. Have a great day.